I don't know why I should record that. People that missed the lecture aren't going to see the video in 6 hours anyway. But we'll repeat it anyway. Within 6 hours, 2 o'clock today, Tuesday, whatever it is, March 6th or 7th? I think it's the 7th. I need to know about not using exam 1 questions. So if you don't want me to use exam 1 questions, you got to let me know immediately. Otherwise, what I'll do is recycle some exam 1 questions. Okay. Chapter 4, don't forget we have hemoglobin and myoglobin. Remember, that was one thing that we kicked off the last exam. It's coming back on this exam. Okay? You are responsible for that, and it's arguably the most relevant for pretty much everybody in the class. Okay? You will see hemoglobin and myoglobin show up on common standardized tests. So definitely go back and review those. I will say that I looked at the slides to write the 2 or 3 questions that I put together, and I'm already considering going into the homework to steal questions from the homework for the exam on the hemoglobin and myoglobin. Just saying. Okay. Chapter 6 was our Michaelis-Menten enzyme kinetics. Chapter 7 was our allosteric kind of kinetics. That's the sigmoidal curve versus our hyperbolic curve. And then some kind of random bits and pieces of active site chemistries. And then chapter 16, I believe it's 16, did I get that right? Yeah. For our carbohydrates. And I think that's it. Try writing a test. It's really not that much as far as test questions go. I struggle to get above 20 questions. And that means you would miss 2 questions and you have a B. So I would prefer to not have it set up that way. I prefer the questions weighted somewhere around like 2 points. And right now I'm having a really hard time making questions. Okay? So that's why I want to recycle exam 1 questions. So it's still testing you on knowledge, but you've already seen them, so hopefully it's easier. I will also say that it is a struggle to come up with questions, so I'm having a really hard time not looking at the old exam to write questions. So when you look at the old exam questions, look at it and say, how can Mike be really lazy and change this question? Because that is exactly what I'm doing. Okay? Yes?
What is the exam on all questions you screen for in front of the multiple choice?
It'll probably just be the multiple choice. I think I can sort of fudge up enough short answer off of this content to build that. Okay, or build at least a reasonable ratio of show your work to multiple choice. Seem reasonable? Okay. So let's get started. So we ended with looking at cyclic structures with really our Fischer projections, and that if we looked at our molecule from the side, we noticed it formed kind of that cycle, or that cyclic structure. Okay. What? So depending on our carbohydrate, we'll end up with either 5-membered or 6-membered rings. Okay. Those get referred to as pyran or furan. I have never memorized that, so I don't expect you to memorize that. But I do expect you to know it when it comes to the homework, okay, which you've probably encountered already. So it's just referencing that as a nomenclature system. When we actually form that ring, we'll be forming a hemiacetal or a hemiketal structure. So today might be interesting. I'm going to have to sit down for this. I don't have my index finger anymore. So if we take a look, yeah, it's going to be really hard. Freaking stupid. So let's erase that for the moment. Let's take a look at the hemiacetal. The acetal we said was coming from, oh, this is really hard, from the aldehyde. Okay. And when we react an aldehyde with an OR, or another alcohol, the oxygen from our alcohol can act as a nucleophile, okay, or an electron donor, which is also a base. In this case, it's going to act as a nucleophile and attack the carbonyl carbon, which will act as our electrophile. The issue with that is that we then have too many bonds at that oxygen or at that carbon that breaks that bond, and through a sequence of mechanistic steps beyond that, doing a bunch of acid-base stuff, which you may or may not remember from OChem, we would end up at this stage. Vaguely familiar? That species is a hemiacetal. Hemi being halfway to becoming an acetal. Well, what's the full acetal? The full acetal, never go, sorry. Instead of having OH, is going to be OR at both positions. So it's, an acetal is kind of like a diether using the exact same carbon. Okay. The carbon that has those oxygen bonds is referred to as the anomeric carbon. Okay. In the case of the hemiacetal, what is special about that anomeric carbon? It's a chiral atom. Okay. How is it chiral? What is causing it to be chiral? I would argue the OH group was actually already present in the structures. That's not really what's causing it to be chiral. I know it's a bit weird. So if we go through, that oxygen was the oxygen from, that's a horrible color. Let's go blue. That oxygen is that oxygen. The hydrogen we started with, and whatever that atom is also already out there. So we started with all those bonds. So they aren't what's making it chiral, which is in air quotes for those of you listening at home. It's the OR group. It's the attacking alcohol. Well, how does that change its chirality? What is the OR attacking? Okay. We could say the carbon of the carbonyl. We can get more specific, and this really digs down deep into the OChem side of it. It's not attacking the alpha carbon, it's the carbon of the carbonyl. What part of that carbon is it attacking? Backside attack would work if we were doing a substitution. We're not doing a substitution. What bond is breaking? The pi bond. What orbitals are used in a pi bond? Where are the p orbitals located? Above and below the plane of the molecule, which means where can that alcohol attack? Either above or below, which generates two different chiral molecules. Okay, technically enantiomers. At that position, they would be enantiomers of each other. Because we get two possible attacks, we get two possible products. And of course, if we have two possible products, we need to be able to distinguish them using their name. Which then means not only do we have D and L, which we talked about, we're also going to introduce a new nomenclature system to identify which cyclic structure we formed. Did our alcohol come in and attack from the top to produce product 1, or did it come in from the bottom to produce product 2? Okay. Which is kind of what this slide is then going to get at, sort of. So we've got the alcohol going to the, or the alcohol and aldehyde reacting to form the hemiacetal. As you might guess, I kind of freak out at that lovely curved arrow that they've shown, because according to that curved arrow that they've shown of the alcohol attacking the aldehyde, we did not break the pi bond. That's kind of a problem, because we'd break the octet. Okay, so we're talking about that. Okay, we'd need that extra arrow. Okay, through a sequence of a couple other steps, which they've also done a piss poor job of showing us, we have to go through a sequence of steps there because it can't be just a direct attack, because what happened to the hydrogen on the alcohol? Is it there in the hemiacetal? Is it attached to the oxygen of the alcohol in the product? No. So it's not just that the alcohol attacked. The alcohol attacked, broke a pi bond, deprotonated, protonated, and then we have the hemiacetal. So there's a lot of mechanistic steps going on behind that. Okay? So that's our general form. What happens as we move to our carbohydrate? Okay, so if we look at the bottom, we're starting with D-glucose. How do we know that that is D-glucose? We look at officially the penultimate carbon, fancy way of saying the second to last carbon, which happens to also be the last chiral atom in our Fischer chain. We look at the functional group of highest priority at that position, which would be the oxygen, and we would say that oxygen is located on the right-hand side of the structure. That means we have D. How do we know it's glucose? That piece matches the structure of glucose. When we then add in the rest of the structure, or the rest of those pieces, we now have glucose.
Does that come from that chart you showed on?
Yes. So I can flip back to that. If you get seasick, you might close your eyes for a minute. Oop. Oh, it wasn't that far back. Yeah, it was. There it is. Okay, now you can open your eyes. See our glucose? Okay, lower left-hand corner. Sorry, the slide projection isn't all the way down. They've added a little bit more information because on this slide they aren't just looking at glucose. What are they looking at? D-glucose. So they've specified that extra position. If we go through and compare right, left, right for those three, okay, back to that seasick thing. What did we say we were looking at? I said we should look at those three, right, left, right. There's our pattern. That's where the glucose name is coming from. There's no rhyme or reason behind it. We just said, well, right, left, right sounds like glucose. Ta-da!
So I was having issues with this in the homework.
Understandably.
So you go back and you just look at the top three for those long changes.
So if you're trying to identify the name of it, and yes, the homework's going to be a pain because it's going to force you to use, I expect you to go back and use a chart like this. So what you would go through and do is within that, whoops, one more. Okay, these are all listing the last chiral atom, D. Okay, so they specified that last one. So we can ignore that one as long as you've established whether you have L or D. Okay. Then what you're trying to do is match whatever else is remaining to whatever structure was given in the homework. Because that's a lovely way to do nomenclature.
Yeah.
But that's what you're expected to do within the homework.
So you just have to match up basically
Yep.
for that bottom row the first three carbons on the whole.
Yes. Okay, unless it was L-glucose, in which case the bottom one switches.
So then for ribo, you just look at the top two.
Ribo, you only need the top two.
If that was not specified as D-ribo, then would you look at all three of them?
Yes. Because you need it, well, it has to be specified as either D or L ribose. Because there's two forms of it. So when it comes to the homework, that question will suck. I'm not going to ask a question like that on the exam. Okay. We did not talk about enantiomers or diastereomers in lecture. Do you want to? Thank you for that little head shake. I agree. I don't want to talk about enantiomers and diastereomers either. Okay. So we don't need to stress about those questions on the exam either. Okay. So we've got our D-glucose formed out. What happens is that that structure then circles back on itself. Okay? And we have a couple options. We could have the alcohol at carbon number 6 attack. But if the alcohol at carbon number 6 attacks, how many atoms would be in the ring? So 1, 2, 3, 4, 5, 6, 7. Is a 7-membered ring stable? No. So that alcohol is not likely to attack. Okay? What if we took the alcohol at position 4? Took that oxygen and had it attack. We have 1, 2, 3, 4, 5-membered ring. Are we allowed to do a 5-membered ring? Yeah. Is there a more stable option? Yes, we can form the 6-membered. So if we have the more stable option, we will go with the more stable option, which is the 6-membered ring. And if we count that one out, and yes, I would recommend you count it 1, 2, 3, 4. There's our penultimate carbon, carbon number 5. The oxygen attached to it can attack. Okay, and that's what they're showing. Remember what we said on the previous slide. What is it attacking? It is attacking the p orbital on that carbon. It can either attack the top of that p orbital, in which case, where does the oxygen of our carbonyl then need to go? Up or down? It'll have to go down. It's going away from the attacking oxygen. If instead it had attacked from the bottom of that p orbital, our oxygen alcohol, or carbonyl alcohol, goes up. So it's all depending on how that oxygen attacks, either from the top or from the bottom. That generates 2 products. Okay? So if we had the alcohol attack from on top, that pushes the carbonyl oxygen downwards. That's what eventually becomes our new alcohol, and this is now down. If it attacked from the bottom, that pushes the carbonyl oxygen up, and we'd have it aimed up. Everybody agree with that? Okay, so I'm going to attempt to draw this relatively fast. Do kind of a quick test here. Jiminy, that's an O. Alpha or beta? Or sorry, down or up, I guess we should say. I heard an oh no. What did you hear an oh no? That will be our correct carbon. This is our anomeric carbon. So you're saying the OH goes down, right? And so what are you complaining about, Jen?
Well, I'm just comparing the position of that oxygen versus...
Position of which oxygen? Give me a little bit more. Give me a little bit more than that.
Oxygen in the ring.
Oxygen in the ring. What's the issue with that?
It's at the bottom, whereas the bottom of the ring structure, whereas in the pictures.
When we assigned up and down, or this top and bottom attack, we were very specifically looking at one orientation on the molecule. And yet, what can molecules do? They can rotate, flip, spin, do whatever. Okay? If I am facing you, my name is, and if I turn around, theoretically, my name should be still Mike. Okay? All that happened in that top structure is I took one of those and I flipped it upside down. Just because the OH is aimed down doesn't mean it's actually down, because I've changed the orientation of the molecule. Everybody kind of see that? Okay. Which way is my thumb aimed? Down. If I all of a sudden turn my hand over, it's now up. That doesn't mean I have a new hand. It just means I've changed how I've looked at the molecule. Which means this up-down relationship that we're looking at really only works when we're looking at a Haworth projection where that oxygen is in the oxygen that's in the ring is behind the plane. Okay? What happens if you have some snarky jerk of an instructor that flips the molecule? Well, then your method of just saying, well, it was down, is completely useless. Okay? I haven't quite decided if I'm that snarky instructor this time or not. Okay? I might be, I might. Okay? So we need a better method to go through and determine where this group is to be able to determine our up and down, or our alpha and beta. Okay? So we've got what are known as our Haworth. We could continue through to draw this in a Fischer projection, okay? Because Fischer thought it would be awesome. Hey, if we've got straight line stuff and we now have a cyclic structure, I can still show that by showing this weird loopy thing. What's the issue with that weird loopy thing shown on the right? What is this? This and this. Those should be carbons. Can they be carbons? No. Why are they shown there? Because it looks prettier if we make it look like a square. This biochemists, okay? Just because it looks pretty doesn't mean you can use that. You're now changing the meaning of what a point is defined as. That adds confusion to the system. I would argue looking at a Fischer projection for your cyclic structures is just stupid. Okay? So I won't test on that. Okay? If you're taking standardized tests, they might test you on that because they're a fan of memorization. And that's really all you're trying to do, is memorize the code on what that looks like so that you can write it down. Okay? So, how can we help to remember our alpha and beta? Okay, when we're looking at our alpha and beta positions, we are referencing ultimately carbohydrates, which means the example I drew becomes a problem because it wasn't a carbohydrate. It was a hemiacetal, but it didn't have enough oxygens to be a carbohydrate. Okay? So what else could I use as a frame of reference within those ring structures to help me say, I know that that one is alpha and that one is beta?
Don't you look at like cis and trans for the CH2OH compared to the anomeric carbon?
What you can do is reference your CH2OH. Okay? And you can compare that to the OH on the anomeric carbon. Okay? And that's what this is now referencing. Alpha means that your OH on the anomeric carbon, or your oxygen on the anomeric carbon, your non-ring oxygen on the anomeric carbon, is trans to the terminal CH2OH. So if we take a look at our far right, we've got our glucose structures. What are they labeling as alpha? Well, there's our OH, there's the CH2OH. The OH is aimed which direction? Down, and the CH2OH is aimed up. There's our alpha. What's the beta? Well, we'll look at those same two positions, and those are now cis. Can this be made more confusing? Potentially. Okay. If I flip the structure, I'll still have cis and trans. And because I'm looking at relative positions to each other, I don't have to worry if the structure is flipping because those will always be cis or trans. I can't do a rotation within the ring. So that's nice. But that CH2OH being aimed up is dependent on something else in the name.
Yeah, that's what I was just going to ask. How can you tell by looking at their ring structure if it's to your own?
The CH2OH being aimed up in your Haworth projection means you have the D sugar.
And that's based off of the CH2OH.
That is based off of, sort of. It is technically based off of the OH when looking at the Fischer projection. What is the problem with looking at the Haworth projection? It's not the Fischer projection. Okay? So assigning D and L based off of the Haworth and saying, well, isn't that based off the Fischer, becomes tricky. Okay? Because if we switch this to the L, what changes? Let's take a look at that top one. What happened to the oxygen that's in the ring? Nothing. So I can't just reference it. What I need to actually be looking at is the CH2OH and how its position is changing.
So the Fischer projections, you look at the OH, the last column.
You look at the OH because of how Fischer is organized. Officially in the Haworth, you're doing the same thing, but you have to realize that when you switch D and L, when you change the location of the oxygen and the hydrogen with each other, your view on the carbon chain changes in the Haworth. Okay. Exceptionally tricky? Yes. That's kind of why biochemists ignore it for the most part and just always focus on the common forms of these sugars, which it typically is the D. Okay. Which is also typical for why they always show things in the Haworth projection, and they try to avoid, as best they can, doing any manipulation that takes it out of that viewpoint. Because the instant it goes out of that viewpoint, our interpretation levels have to skyrocket for what is happening within the molecule. So you will see some very goofy looking drawings when we look at polysaccharides. Right now we're just monosaccharides. You'll see goofy drawings how we're linking things together, because what they're trying to do is make sure they don't change your viewpoint on the Haworth projection. Because the instant you change the viewpoint, now you actually have to interpret the structure. You have to do work. By God, that's amazing, biochemists. Okay? And yes, it is challenging. That's why we try to design systems that prevent us from having to do that work. Okay? The issue with that is it removes a structural understanding. Okay? Which a student that was pushing for the MCAT took this a step further and said, okay, there's got to be some other sense behind why we're referencing these as alpha and beta. And there is some more sense to it. Which comes first, alpha or beta? Alpha. Guess which was discovered first? Alpha. Why are we calling them alpha and beta? We discovered alpha. We're like, oh, this is what it looks like. And then someone did some more research and said, well, wait, this glucose is different than that glucose. Oh, we have a second form. Well, what do we call two things? We could call them form 1 and form 2, but that starts to reconcile too much back to nomenclature systems and locations, and we don't want to reference that. So we'll throw in Greek letters. There's our alpha and beta. Okay. So there's an interesting question. Why would we have discovered alpha first? So that's getting too structural. So these terms ultimately came about probably before we even knew what atoms made these structures. Common's not a bad idea, but I don't think it's a common thing either. Which are you more concerned about, hydrochloric acid or acetic acid? Why hydrochloric?
Because it feels best for the human body. More acidic.
More acidic, meaning it's more, begins with an R, reactive. Why did we discover the alpha one first? It's more reactive than the beta form. Okay, where's the most reactive site in both those molecules? I'll kind of accept first carbon, but it's only a first carbon because this is an aldose. Where's the most reactive carbon? As a hint, it reacted to make these. The anomeric carbon is our most reactive carbon. It is this carbon. That's the reactive one. Okay. What's going to be reactive at that carbon? Oh, really fun next door. Yes, Mark, exactly. The OH. Okay? The OH is going to be the most reactive part of this. Okay? That is the most polar part of this. The more reactive that OH becomes, the more likely the anomeric carbon starts to react. Okay? So what am I getting at then? Why would I be looking at that OH? Can that OH be more or less reactive? Yeah. Okay. What are you thinking?
Depends on whether it's axial or equatorial.
It's an axial versus equatorial thing. If we take a look at our structure, we have a six-membered ring. Six-membered rings adopt chair conformations. What happens when we look at the chair conformation? So there's a chair. Let's just go through and define this. Here's our oxygen. Okay, we've got our anomeric carbon. Where would I like to have that OH? Axial or equatorial? Okay, equatorial. Okay, we now have to backtrack out to find our CH2OH. Our CH2OH is going to be located at which position? There's our CH2OH, right? Or that's where our CH2OH should attach. Where would I prefer to have the CH2OH? Equatorial. It's a large group. So I would like to have that in the equatorial position. CH2OH, right? Which structure do I have? Alpha or beta? Where's the alcohol, the red alcohol aimed? More up or more down? Down. Where's the CH2OH aimed? More up or more down? Down. If they're both down, that makes them cis, which makes them beta. This is the most stable form for our glucose structure. And whether this was D or L, sorry, I may have goofed that one up, so we'll ignore that. Okay? But this is our most stable form. Being the most stable form, what are the odds I'm going to be able to get it on its own? Not very likely, which means, what are the odds I'm going to be able to discover this one? Not very likely. What happens if we switch to the alpha form? We said they're trans, which means... that was not a happy laugh. Particularly because I had a nice looking chair and now it looks like crap. And I lost all my color coding. What a perfect day. Now what's the relationship of the OH and the CH2OH? They're trans, and that matches alpha. Is this structure more or less stable than the previous form? Less stable, which means it is more reactive, more likely to be discovered. Kind of neat. Believe it or not, when the student mentioned this to me, I just kind of ignored him and said, I don't really care. I've later regretted that decision. Because this is pretty neat observation. Where do we use carbohydrates? So you all read up on these. Where do carbohydrates show up? Two common places. Two common roles. Let's try roles. Energy. Which form are we going to use for our energy? Why the alpha? Because it's easier to react. I want to use the alpha form for all of my energy needs because I want to be able to get access to that molecule. I do want to store it, but I do want to be able to later get access to it. What's the other role for our carbohydrates?
Structure.
Structure. Do we want to be able to access the structure? No, we want it locked up and immobile and not reactive. Which form do we use for structure? beta. Okay? So the rest of the chapter then goes through and says, well, we use alpha forms for all these different energy needs. Energy storage is still the same concept as just energy in general. We want the reactive form. The reactive form will be our alpha. Okay? Then we see a variety of other carbohydrate lists or polysaccharides and go, oh my gosh, they're all used for now structure. Well, those are completely opposite dynamics. That makes no sense to use a molecule that you want access to for energy to then also generate structure. It all comes back to the alpha versus beta relationships. Okay? So I thought that was kind of a neat observation when I came across it, or eventually processed it, spent some time to think about it. Okay? I personally think that makes it easier to memorize the relationships, okay, between alpha, beta, and then their different roles or their different functions for carbohydrates. Okay? Haworth projections. Okay, kind of just assumed you knew what was going on with it. Are you guys familiar with what it means to be in a Haworth projection? Okay. I don't officially accept your answer, Jen, just because I explained it to you in OChem. Everybody else, you get it, makes sense. When you look at a Haworth, you're like, the bottom part is coming at you, the back part, the solid lines are going away from you, and that's the definition of your Haworth. Up, down, just those groups are aimed more up or more down. It's an attempt to simplify the chair conformation. Okay, yeah?
So on the test, are we going to have to go from Haworth to Fischer?
No. So we said Haworth, Fischer we won't do.
Okay.
Absolutely not. Haworth to a chair, arguably. Yeah, arguably. I don't know if I would do that. Hopefully I'll forget by the time I need to write some more questions.
That'd be nice.
But yeah, you're definitely responsible for that part. So if we go through and then compare everything, we've got our Fischers, we've got our Haworths, and then we have an abbreviated Haworth. What's happening when we move from the Haworth to the abbreviated Haworth? We just ignored the hydrogens on our carbons. Okay. That can just clean it up a little bit. But you can kind of go through and see those relationships and how they're set up and established. It's kind of a big mess, in my opinion. Because it's such a big mess, I wouldn't stress too much about it. But you, in theory, should be able to pick out those patterns on recognizing your alpha, beta, DNL, all that fun stuff. Kind of makes sense? Okay. Reactions of our monosaccharides. Our monosaccharides will get referred to as reducing sugars, which is a pleasant term if you remember from your redox chapters in either 130 or 151. When we say reducing, what does that mean? You're getting to the sugar part, but let's avoid the sugar part for the moment. What does it mean to be reducing, just in general? If something is reducing, what is it doing? If it is reducing, it is causing something else to be reduced, which means it was oxidized, it was losing electrons. Yeah, you may not like that, but that's what that ing means. Okay? A reducing sugar is one that reduces an oxidizing agent, meaning the other species was reduced. If the other species is reduced, what happened to it? It was oxidized. Yeah. Okay. Which theoretically should be reviewed from your 130s or 151s if you went through and did those. Most people just try and ignore that, memorize it as quickly as possible, and move on. Okay? So your reducing sugar is one that is oxidized, okay, or is oxidizable. Okay? For it to be oxidizable, it needs to lose electrons. Well, that definition is going to suck. So let's see if we can come up with a better one. Okay? To be oxidizable, we are increasing the amount of oxygen bonds. Okay? So a reducing sugar is one that can have more oxygen bonds. So let's take a look at the sugar at the very bottom. Okay? Our reactant. Was that sugar oxidizable? Well, if we look at the reaction, what happened to the amount of oxygen bonds in that structure? It increased. So was the sugar oxidizable? Yes. Which means it was a reducing sugar. Okay? Yes, that's very cyclic and irritating, but that's the way it works. Okay? So what characteristics of that molecule allow us to say that it is oxidizable or a reducing sugar?
Is that where that comes in, the availability? Like it has an available acetal or aldehyde? Is that what? I
So,
was trying to do that from the passing sensation.
yes,
So,
and
making that up
it's a challenge. Okay? So let's take a closer look. What position reacted? Number one, the anomeric carbon. Cool. The anomeric carbon is our reactive carbon. Okay, that's the one that we're referencing when we're referencing this whole reducing or oxidizable, all that fun stuff. So we're talking about that carbon. Okay. The other carbons, while potentially oxidizable, are not reactive enough that under biological conditions we won't see those oxidize easily. Okay, so we're really only referring to the anomeric carbon. Okay, and I believe, Mark, I heard you say something about an aldehyde. Where's the aldehyde? I don't see any aldehydes, right? Wait, what kind of form of the sugar are we looking at? A what? We're looking at the acetal form, or the hemiacetal. Where do we get a hemiacetal from? From the... I think I left that off. The aldehyde. Is there actually an aldehyde in that Haworth projection? Yes. It is hidden in the chemistry of the acetal, which is very easily reversible reaction. We do have an aldehyde there. Is an aldehyde something that we can oxidize? Yes. Okay. So we have a couple approaches to this. Number one, we can always look at our Haworth and say, okay, let's turn it into whatever the carbonyl is. What if it had been a ketal? What changes about our structure? What change would I need to modify to make this a ketal? So the anomeric carbon is the one that is our carbonyl. Okay. If it is shown as is, it is the hemiacetal. What makes it the hemiacetal? What makes it the ketal? I guess I should add the hemi on front of those. In line format that had an aldehyde, what in looking at the Haworth makes you go, that is an aldehyde? How do you distinguish an aldehyde from a ketone? Oh, fun. We could turn that into a little quiz question. I could make that, that's an easy exam question. That's cool. I'll do that. What, when looking at the structure, makes you go, it's terminal? What's the extra thing out there? CH2OH is an alcohol. What's the abbreviated form for an aldehyde? Line formula. Jen, this C what? H-O. When we're looking at that Haworth projection, how do we know we have an aldehyde? There's a hydrogen there. When we make this a ketal, what's that hydrogen? a CH3 or a CH2OH. It's a carbon. Okay? If that is a carbon, when I take it to the ketone, can I oxidize the ketone further? No. So one of the things that we'll be looking for our reducing is that we must be an acetal, must be an aldehyde. Okay? That aldehyde chemistry is buried, so that's where we have to see the hemiacetal functionality. Okay? And it's coming down to the presence of that hydrogen being of critical importance. Because when I oxidize, what do I need to do? Increase the oxygen bonds by removing hydrogen. I have to be able to remove a hydrogen. If I don't have that hydrogen, I can't do the oxidation at that position, and it will by definition not be a reducing sugar. Kind of get it? Is there something else that is important for this oxidation reaction to occur? What else do I lose in the process of this? I don't lose water. I lose, what's that? I lose the other hydrogen on that alcohol. Okay? So to be a reducing sugar, I have to be able to remove two hydrogens. One hydrogen has to be located at the anomeric position. The other hydrogen will be attached to the oxygen. So if I have a ketal, freaking eraser, or a hemiketal, is this now a reducing sugar? No, I don't get a reaction to occur. No product. Let's say I still have that as a hydrogen. But now instead of this being OH, it's OCH3. I can't oxidize this one either. Okay. What form of the structure do I have now? Is this a hemiacetal anymore? No, what is it? What did hemi mean? Hemi meant half. So it was half an acetal before. What is it now? It's a full acetal. Okay? In the full acetal, it is fully protected, and it doesn't react. So you may remember from organic chemistry looking at acetals as protecting groups. They prevent reactivity at that position because they've removed one of those hydrogens. It prevents oxidation reactions. Okay? So when we're looking for our reducing sugars, we're looking for a hydrogen at the anomeric carbon and an alcohol at the anomeric carbon. If those two conditions are satisfied, we now have a reducing sugar.
Can you repeat that? You said an alcohol, or an OH and an H?
We need an OH and an H at the anomeric carbon. Relatively good? Okay, let's see. Do I get a fancier sugar? I don't get a fancier sugar there. Because I'm just thinking of the practice test. Which is going to become a big thing. We had to identify an H and an OH. Is that an H? Was that an OH? The biggest trick when looking at our carbohydrates is not just identifying what these pieces are, it's identifying where they are located. They must be located at the anomeric carbon. How do we know we have an anomeric carbon? It can't be OH because I've circled an OH. I don't accept that. OH off the ring. Okay, let's try an OH off the ring. Shucks. Okay, I heard chiral carbon. How many of you loved chiral carbons? Okay, so yes, that's true, and no, actually, I lied. It's not true, because all of those positions are chiral. So chiral carbon doesn't help us out. Having an OH on the ring doesn't help us out. How do we know we have the anomeric carbon? It's the first carbon. When you count, what do you start with? 1, 2, 3. Is that the anomeric carbon? No. Your first carbon can be anywhere you start counting, so I don't accept that. Relative to the oxygen. Okay, so you mean 1, 2, 3. Okay, why do I have to go the other way? This is identifying what that anomeric position is. Because everything you've given me so far assumes this is your structure, that it is organized in this fashion. It's not always looking like this. We need to be able to look at any structure and any orientation and say it is always that position, because you should be able to do that.
Is it because of the oxygen in the ring is pulling more electrons toward this, so that OH is more reactive?
That doesn't allow me to differentiate that position. So you are all telling me that this is the position. I want to know what is characteristic about that position that no other carbon has, because that is the anomeric carbon.
Does it have to go back to the Fischer projection?
Nope, don't even need that. Okay, so we could go off the hemiacetal. So instead of using the word anomeric, you're using the word hemiacetal. Okay, why is it the hemiacetal? I don't see an aldehyde. I don't accept that either. Say that again.
The OH and OR group.
It is the only carbon in this structure that has what two things attached to it? Oxygen. Every other carbon in this structure has how many oxygens attached? 1 and only 1. The anomeric carbon will have 2 oxygens bound. Because when we break it, what does it come down to? It becomes a carbonyl. And a carbonyl carbon has how many bonds to oxygen? 2. 1 being sigma, 1 being pi. Your anomeric position will always be a carbon with 2 oxygens bound to it. Always. Okay? Does that make sense? And just because we said that a whole bunch and you guys are all writing that down, let's go ahead and do it here. Our anomeric has 2 oxygens bound. Well, that's pleasant. Okay? And that is huge. Pretty much everything we do within carbohydrates is identifying that anomeric position. If you can't find the anomeric position, the rest of it is useless. Okay? You need to be able to find that position.
Would that have anything to do with, like, you know, when, like, over time we do priorities, where that one's attached to 2 oxygens, would that make it the highest priority?
That would make it the highest priority, which means when we move to the Fischer projection, it's at the top. Yep. And if we go back to those slides and we look at the Fischer projection, they're marking the red OH, which is kind of bad. They should actually be marking the carbon, because the carbon's the important position. The red OH is located at the anomeric carbon. Where's the anomeric carbon in our Fischer projection? It's at the top. Okay? So it's trying to find those patterns and nail those patterns down so that you can then identify all those pieces. Kind of makes sense? Okay. What happened in these cases is we moved from, these are actually 2 examples. We're going from D-sorbose to D-sorbitol and xylitol to, oh, it's actually going inwards. This is a division between those 2 separate examples. The word on the far right going to xylitol, or sorbose. Sorbose? Is that right?
That's right.
Going to sorbitol. What's happening? what changed on those carbohydrates as we go to the middle? What did you say, Jen?
Reducing?
It's reducing?
Well, it's oxidizing.
What I would try my best to do as a student is avoid the use of ing. Because the instant you say ing, you're now referencing the opposite feature. Okay, this goes back to reducing agents and all that fun stuff. So what happened to sorbose to become sorbitol? It was reduced because it lost oxygen bonds. Okay. This would make it a reducing sugar? No, because a reducing sugar was oxidized. Here it was reduced. So this is not a reducing sugar, it's... Yeah, we could go with non-reducing. I would accept that. What's our other option? It's an oxidizing sugar. All sugars are going to be oxidizing, which is why they don't put it in as a special classification. Because we can reduce a carbonyl. And since all carbohydrates have carbonyls, we'll be able to reduce those. Every single one of those.
Can you explain the difference between non-reducing, in the practice exam?
Yes.
Yes, reducing, non-reducing.
So reducing and non-reducing are referring to, oh, it's having fun connecting. Reducing and non-reducing are referring to the ability, and because it's not connecting, I can't change slides. Keep trying to reconnect. Oh, it won't even let me close out. Reducing and non-reducing are referring to the or your anomeric carbon. Okay. If your anomeric carbon, and really neither shouldn't have been included, if your anomeric carbon can be oxidized, you have a reducing sugar. Okay. If your anomeric carbon cannot be oxidized, you have a non-reducing sugar. Okay. The neither condition is really non-reducing, I believe. I think I'd have to go back and take a look, but it might have just been me making something up, so I had more than a true-false question. And our internet connection has completely died, which means I believe the next sequence of slides are just a bunch of facts, so unfortunately if you watch from home, you just got to read them.